What's going on, Algebra Bros? It's Mr. C here, and in this video I'm going to show you how to analyze the graph of a polynomial function using a step-by-step process. So the function that we're going to be analyzing is this one. It's a polynomial function in somewhat of a factored form, and step 1 wants us to determine the end behavior of this function's graph. So for that, what we're going to need to do is determine the leading term. It's given by a sub n x to the n. And with the polynomial function in this somewhat factored form, it's not really helpful. So what I'm alluding to is that, what we'll want to do is multiply everything out to get a better idea of what that leading term looks like. So let me just jot it down again. X squared times x plus 2, x minus 2. And my recommendation would be to FOIL the x plus 2 times x minus 2 with each other. Excuse me. That gives us x squared times quantity x squared minus 4. And then we can go ahead and distribute the x squared to clear parentheses. And we get a final result of f of x in standard form as x to the 4th minus 4x squared. And so this makes it a little more clear as to what the leading term is, and that leading term would be x to the power of 4, which I'm going to go ahead and take that out of context. I'll write x to the 4th, and the leading coefficient is kind of a secret ninja 1, which I'll include as well. And I do want to note that the 1 is a leading coefficient that's positive, and the 4 is a value of n, the degree, that's even. So based on what we know about the 4 possibilities of end behavior, when this graph is drawn out, we should have one end pointing up in quadrant 1 and the other end pointing up in quadrant 2. And this would be acceptable as an indication of end behavior. Now we're going to move on to finding the x and y intercepts. Excuse me. Let's start with the x-intercepts. So I'll make a little workspace for that. To hone in on these x-intercepts, we have to set up the following equation. F of x equals 0. And the version of f of x that I recommend you using is the partially factored form. So x squared times x plus 2 times x minus 2 equals 0. And I'm going to factor this fully, i.e. rewrite x squared as x times x, and then bring in the rest of the stuff. So since the left-hand side is completely factored, and the right-hand side is 0, what we're going to do with each factor is set it equal to 0 and solve for x. So we get a pair of x equals 0 equations. We get the third equation, x plus 2 equals 0, which gives us an answer of x as negative 2. And then we have x minus 2 equals 0, which gives us an answer of x as positive 2. So one x-intercept is 0, 0. Another x-intercept is negative 2, 0. And a third x-intercept is positive 2, 0. So this graph appears to have 3 x-intercepts, and hopefully that's something that we see when all is said and done. Let's talk about a y-intercept. If this graph has a y-intercept, which it should, it's going to be found by doing f of 0. And you can use whichever version of f of x you prefer. I'm going to go ahead and use the initial version. So plug 0 into x. First factor looks like 0 squared. Second factor is going to be 0 plus 2. And then last factor is going to be 0 minus 2. So that's going to be 0 squared times 2 times negative 2. 0 squared is 0. And when you multiply all three of these numbers out, you get 0. So this graph's y-intercept is 0, 0. So we have both an x-intercept and y-intercept at the origin. By finding the x-intercepts, we actually are able to give an immediate answer to one of the parts for step 3, where it says determine the zeros of the function. But we also want to know what their multiplicity is, and based on the multiplicity, determine whether the graph will touch or cross the x-axis at the x-intercept. So let's talk about the zeros. The zeros are actually something that we found back in step 2. We have x equals 0 as a 0. We also have -2 and +2. Do note, though, that x equals 0 showed up as an answer twice, so it has a multiplicity of 2, which I'll indicate that right after writing the 0 out. So we'll say mult 2. And because it has a multiplicity of 2, and 2 is an even number, what the graph is going to do is it's going to touch the x-axis at that x-intercept. Another 0 was -2, and looking at our work from step 2, -2 showed up as an answer one time, so this has a multiplicity of 1. So we'll say mult 1, and 1 happens to be an odd number, therefore the graph is going to cross the x-axis at this x-intercept. Last but not least, we have a 0 of +2, and based on the above work, it showed up as an answer one time, so it has a multiplicity of 1, just like -2 has a multiplicity of 1. And again, because 1 is an odd number, what this graph is going to do at the x-intercept of 2 is it's going to cross. Right, and that's where the pain and torture, the fun and excitement ends for step 3. Moving on to step 4, it says use a graphing utility to graph the function. And what you would do here is simply enter f of x into y1. And you can use either the partially factored form or the standard form version of f of x. I'll hang with the partially factored form. So, if it were me, in y1, I would enter x squared, then quantity x plus 2, then quantity x minus 2. What this is going to do is produce a graph that kind of looks like a W. And because it looks like a W, you can clearly see that there are going to be 3 turning points. So I won't include the graphing calculator work here, but I'll kind of leave that up to you guys. If you look at step 5, it says approximate the turning points of the graph. And based on even this little schematic, we have a turning point right there, a turning point right here, and a turning point right there. And just do keep in mind that turning points are basically the maximums and the minimums. So I'll say maxes and mins. And by using the minimum and maximum features of the graphing calculator, I arrived at the following as turning points. One turning point is at approximately -1.41, -4. Another turning point is at the origin, 0, 0. And another turning point is at +1.41, -4. And I do want to kind of qualify these turning points. For instance, the first turning point can be classified as a local min, but also an absolute min. 0, 0 can only be classified as a local max, whereas the last of these turning points can be classified as both a local min and absolute min. So at this point we have enough information to sketch our graph on our own. So we'll bring everything together and place it in the coordinate plane and just verify some of these results. First of all, we do have an idea of where the x-intercepts are at. One x-intercept is at -2, 0. Another x-intercept is at 0, 0. And then a third x-intercept is at 2, 0. We also know that there's a y-intercept at 0, 0. That's probably clear to see. We know that there's a turning point at -1.41, -4. So I'm going to go roughly halfway between -1 and -2, and then down by 4 units, like a g-unit. And then positive 1.41, so I'll go halfway between +1 and +2 roughly, and then go down to -4. And then of course, we have that middle turning point at the origin, 0, 0. So lots of action going on at the origin. And now what I'm going to do is just connect all these points together, keeping in mind the end behavior and turning points and intercepts. So one end of the graph is going to be pointing up in quadrant 2, and as we go from left to right, it's going to decrease its way through the x-intercept of -2, 0. Keep in mind that this turning point is both a local and absolute minimum, so from there on out it should start to increase, and then the turning point of 0, 0 is a local maximum. And then we have another local doubling up as an absolute minimum at 1.41, -4. We should go through the x-intercept of 2, 0, and then remember, with the end behavior, both ends should be pointing up, so there should be an end pointing up in quadrant 1 as well as quadrant 2. Now I do want to point out that the graph is crossing the x-axis at -2, 0, which is something we predicted back in one of the earlier steps. The graph is touching at 0, 0, which is something we also predicted. And then the graph is crossing at 2, 0, which is something we also predicted. So there's our graph. Let's move on to analyzing it a little bit further. Determine the domain and range. By default, the domain of any polynomial function is all real numbers. That's because you'll never have division by 0, nor negative numbers inside of even roots, such as a square root. Now the range isn't all real numbers. Actually, there is a smallest y value on the graph, and that would be indicated by these absolute minimums, doubling up as local mins. The range is actually going to start at -4, and because both ends of the graph point up to positive infinity, the rest of the range should indicate that. So the range is bracket -4, comma, infinity, and by default, parentheses on infinities. As for increasing and decreasing, if you trace this graph from left to right, the behavior that you start out with is decreasing, and that part of the graph that's decreasing happens on these x values from -infinity to -1.41. So you're decreasing until you reach all the way down to this absolute minimum of -1.41, comma, -4, and then you increase for a little bit. So the x values that will correspond to that part of the graph that's increasing go from -1.41 to x equals 0. So you reach the local maximum, and then you have to, or then the rest, or and then the next part of the graph, sorry, is decreasing between the x values of 0 and positive 1.41. So I'm going to union this piece for decreasing with parentheses 0, comma 1.41, and then you reach this second absolute and local minimum, and then the rest of the graph increases from there on out, and that's going to happen between the x values of 1.41 and positive infinity. And that is a complete analysis of the graph of this function f of x, and that's where I'm going to cut the video. Of course, if you guys have any questions whatsoever, feel free to let me know. Otherwise, thanks for watching the video, and I'll see you guys in the next one. Have a good day.